Right, we just did a topic looking at algebra, basically. But the other part of mathematics, I guess, is not just so much the algebra, it's the actual arithmetic with numbers itself. So this one focuses more on numbers themselves. So the real number system, which is what we work with. So imagine we've got the set of real numbers. It contains every number that you've worked with so far. What is a real number? A real number is anything that can be placed on the number line. That's why the number line is sometimes called the real number line. Okay, so anything that can be placed on there is a real number. The symbol for real numbers is the hollow R. So it's not just R, it's the hollow R. Now, inside our real numbers, we have the rational numbers. Rational numbers, which of course are labelled Q. Can't use R because we just used it for real numbers. Q. Now, why Q? Q stands for quotient. Right? So if you think about it, a rational number is any number that can be written as a fraction. Then we have the irrational numbers, the ones that can't be written as a fraction. Now, there actually isn't an abbreviation, but a way of writing it is like that, R\Q. The backslash means not including. So it's the real numbers, not including the rational numbers. So you're left with the irrational numbers. Hardly ever see that notation, to be honest. But if you had to come up with one, that would be it. Okay, let's go back to the rational numbers. Can't do much else with the irrational. So back to the rational. Inside are fractions. You know, if you think, well, they're all fractions. So by fraction, I mean anything that can't be simplified down to a whole number. So I'm not considering something like 4/2 as a fraction, because of course that could be written as 2. So anything that can't be simplified down, we're calling a fraction. We then have the integers, the ones that can cancel down to whole numbers. And of course, as you would realise, the symbol for integers, no, it's not I, it's Z. It comes from the German. So Zahlen is the German word for integer. And I don't know how much you know about the history of mathematics, but you go back to 17th century, 16th century, around about then. But the two big groups in mathematics discovery in those days were the English and the Germans. It brings up the calculus debate between Isaac Newton and Gottfried Leibniz, who actually created calculus and things like that. But anyway, that's a story for another day. Okay, so we have our integers. Speaking of the natural numbers then, symbolised N for natural. Natural numbers, also known as counting numbers, also known as cardinal numbers. Basically, well, if I call them counting numbers, it's obvious what they are. Because if I said to you, start counting. See, you started at 1. So you go 1, 2, 3, 4, 5, 6, positive integers. 0 sits by itself. It's a very strange number, 0. Some people say it's not a number because it doesn't exist. It's nothing. Right? It's simply there to hold place value and things like that. 0 does weird things. Remember that question, 0 to the power of 0. What's going on there? So, but it is there inside our real numbers. But then overlaying all of that are the negatives. So you can have negative fractions, you can have negative integers, you can have negative irrational numbers. But notice it doesn't overlap the natural numbers. You don't have negative natural numbers and, well, negative 0. So there is our set or our family of numbers that we work with. Prime factors. Okay? Every natural number, so positive integer, can be written as a product of its prime factors. So for example, 324, we want to break it down. We go, oh, okay, two things multiply together. 4 and 81, but each of those can be broken down, of course. And we end up with 2 squared times 3 to the power of 4. We bring it down to its prime factors. Highest common factor. Well, to work out a highest common factor, you get both numbers, write it in terms of its prime factors. Then take out the common factor. Let's have a look at these two numbers. 1,176, which is 6 times 196. 3 times 2 times 49 times 4. 3 times 2 cubed times 7 squared. That's as far as we can go. 252, 463s, 4 times 9 times 7, 2 squared times 3 squared times 7. How do you find the highest common factor? It is just like factorising algebra. It's exactly the same. It's like imagining those two things were in parentheses. I want to pull out a common factor. So it would be 2 squared times 3 times 7, because when we factorise, you always remove the lowest power that's in common. So in this case, we pull out 2 squared, not 2 cubed, and we pull out 3 to the power of 1 and not 3. That brings up lowest common multiple. So again, we write it in terms of its prime factors. Then we write down all the factors without repeating. So make the numbers a bit smaller, 48 and 15. 48, 16 times 3. 2 to the power of 4 times 3. 15 is 3 times 5, and that's as good as it goes. There's our lowest common multiple. This is the same as when we were dealing with fractions and trying to work out the common denominator. It's basically, if it's not there, put it down. Same idea. So we use the highest power in this case, 240. Let's see how good we are. Of course, if you're getting quick, you get the easy ones. And that is divisibility tests. Very handy when you're trying to factorise, so you're trying to find, okay, what number combinations will work. How do you know if a number is divisible by 2? Oh, very good. You got the easy one. Even number 3.
Sum of digits is divisible by 3.
Correct. The digits add to a multiple of 3. 4. Last 2 digits are divisible by 4. Oh, you're going to have to get quick for this one. 5, anyone?
Last digits are 0 or 5.
Last digits are 0 or 5. 6. Good. Because then it's divisible by both 2 and 3, thus divisible by 6. So it's divisible by 2 and 3, satisfies both of those tests. Oh, now we're going to be going good. 7, anybody? This is where we always get the pause. 7. What is the divisibility test for 7? No cheating. All right, here we go. Double the last digit, subtract it from the other digits, then look at the answer. And if it's divisible by 7 as well, you're in business. Let me show you. Give me a number that we know is divisible by 7. Was it 105? 105, okay? Double the last digit. The last digit is 5. Double it, you get 10. Subtract it from the others, you get 0. And 0 is, of course, divisible by 7. Therefore, that's divisible by 7. Give me another one. Go for a big one if you like. Get your calculator out in case you can't work out one.
7,203.
Say that again. 203, did you say?
7,200.
Is that divisible by 7? Oh, it is too. Okay, because double the last digit, you get 6. Subtract it from 20, you get 14. 14 is divisible by 7, therefore 203 is divisible by 7. 107. 567. 838. What do you have to do? You have to have a lot of patience. Okay? Because you go double the last digit, you get 16. Subtract 13 minus 6. What's 13 minus 6? Oh, what a coincidence. 7. 8 minus 2 is 6. 7, 6, 5, 7, 0, 1. Double the last digit, 14. 6 minus 4 is 2, 6, 5, 7, 0, 1. Double the last digit, 6 minus 4 is 2, 6, 5, 7, 0, 1. Double the last digit, 4 gives us 2, 5, 7, 0, 1. Double the last digit, we're getting there. 5 minus 4 is 1, 7, 0, 1. Double the last digit is 2, 1, 0, 5. Double the last digit is 10. We have 0, and that is divisible by 7. Okay? So you do get there in the end. All right, let's move on to the next one. 8. Yeah, now we get back to easier ones. We just look at the last 3 digits. 9. What is it? And I guess that's because 9 is 3 squared, so you get a similar sort of 1 to 3 is ready for this one. 10, anybody?
The last digit is 0.
Oh, very good. Which now brings me to the next challenge.
Oh, 11.
11. Oh, you know this one. The number is palindromic. 434. Is that divisible by 11? No. Okay. Just give someone else a go, see if they got it.
It's like the digits on the outside add up to 11. Add up to the one in the middle.
I think you're on the right track. Let me put up. Okay. The sum of the even position digits equals the sum of the odd position digits, or will differ by a multiple of 11. All right, give me a number. 5. Okay, I should have been a bit more specific there. Give me a number divisible by 11. 14,601. Oh, 14,600, which, by the way, happens to be palindromic. Okay. The sum of the odd positioned digits. 1, 6 and 1 is 8. The sum of the even positioned digits is 8. There you go. They equal each other, so it's divisible by 11. I think I stopped there because I didn't have any more room. But there are tests for 12 and so on and so on and so on. Quite interesting. Okay, handy, as I say, when you're trying to factorise and things like that. Yeah. All right, let's move on. So fractions and decimals. Look, converting a fraction into a decimal is incredibly easy because the fraction tells you how to do it. Top divided by the bottom, you work it out, there's your decimal. Easy. Going back the other way. If it is a terminating decimal, again, very easy because we have a base 10 system. And so we know, 0.62 will be 62 over 100 and things like that. Easy. It's the ones that don't terminate, the ones that go on forever, which may be irrational, in which case there's no way of working it out, or it might repeat. Converting recurring decimals into fractions, how do we do it? 0.6 repeater, I purposely pick one we should know straight away what it is anyway. We can do it with algebra, because of course 0.6 repeater is 0.6666666 and so on. So let x equal that. That means x is 0.6666666. Well, if I multiply it by 10, I get 6.6666666. We do a subtraction, and 9x is 6, x is 6 on 9. Therefore, 0.6 repeater is 2/3. If there's more than one number repeating, 0.81, which goes 81, 81, 81, 81, 81, 81, 81. Let x equal 0.81, 81, 81, 81, 81, 81, 81. Multiplying by 10 here is not going to work, because the idea is we want to get the same thing behind the decimal point, so that will cancel, and I'm just left with numbers and I can play with it. But if I multiply by 100, I can get the same number behind the decimal place. So I do a subtraction, 99x is 81, 81 on 99. Oh, that simplifies down. 9/11ths. What happens if not all the numbers are repeating? So 0.327, which is 0.3272727272727, and so on. Well, if I multiply by 10, no, not going to work. Multiply by 100, look what happens. Whilst the number is not the same behind the decimal place, if I go to one decimal place, they are now the same. So I can still do this idea, I just get something strange. 99x is 32.4, so x is 32.4 on 99, but we don't normally have decimals in fractions. Multiply top and bottom by 10, and you get 324 on 990, which, by the way, simplifies down to be 18 on 55. Now, that's how mere mortals do it. Very inefficient, really inefficient. But I don't know if they were for some reason to say use simultaneous equations to find this, then all right, that's how you do it. How can you tell by just looking at it? 0.6 repeater. By the way, when it's one number, it's real easy because each one's a ninth. 0.1 repeater, 1/9. 0.2 repeater, 2/9. 0.9 repeater is 1. Things like that. Okay. By the way, 0.9 repeater is 1. You did know that, didn't you? It is the same thing, 0.9 repeater 1. Okay, how do I look at it? What's the number that's recurring? 6 is the number that's recurring. So I put that on the bottom of the fraction. How many numbers are recurring? Well, only one number's recurring, so I put 1 9 on the bottom of the fraction, and there's my answer, 6 over 9. 2/3. Applying that same idea to the next one, 0.81 repeater. What is the number that is recurring? Well, 81 is the number that is recurring. How many numbers are recurring? Well, there are 2. So I'll put 2 9s on the bottom. By 2 9s, I don't mean 18. I mean 99. We put 2 9s down. And there's your answer. So if I had 0.7134, and they're all repeating, there's your notation, by the way. You don't put dots over every number. First number that's repeating, last number that's repeating. That's where the dots go. Some people put a bar over all the numbers that are repeating. What's the number that's repeating? 7,134. How many numbers are repeating? Well, there are 4. So I'll put 4 9s down. There's your answer. Simplifies down. There we go. Much more efficient and quick. What about the ones where not all the numbers were repeating? Okay, here's how we create it. 324 goes on the top. Why? 327 minus the one that's not repeating. So 327, 3 is not repeating, so I'll subtract it. 324. What do I put on the bottom? I put 990. Why? 2 numbers are repeating, so I put 2 9s. 1 number's not repeating, so I put 1 0. It would be stupid to put the 0 at the front of the number, because then it would just be 99. So you put the 0 at the back of the number. There's your answer. So if I had this, 0.1096, and only the 9 and 6 are repeating, 1086 goes on top. That's 1096 minus the ones that are not repeating, which is 10. And on the bottom, 9900. 2 numbers are repeating, 2 are not. I love the fact people don't believe me, but that's good. They are checking it with their calculator. You can't be right. Surely it's not that quick. There it is. There's our first bit of theory for today. 2A. And I threw in from the old Cambridge too. There were some nice questions there I thought we'd add.